So welcome to the third lecture of this afternoon in section of Combinatorics. So I have the pleasure of introducing Peter Keevash. Peter got his PhD at Princeton in 2004 under the guidance of Benny Sudakov. After that he was at Caltech and then Queen Mary in London. And now since 2013 he has been a professor at Oxford. Peter has done great work in combinatorics, and for people who have contributed to lots of things, when you kind of think of picking one, it's usually difficult. But there's one thing that Peter did more recently that really stands out, and that's the proof of the existence of designs. And I'm sure we'll hear a little bit about that today. Today he talks about hypergraph matchings and designs. Peter.
Thank you. It's an honor to be here. I plan to tell you a bit about hypergraph matchings with particular emphasis on characterization of the perfect matching problem in dense hypergraphs and the existence of designs. So let me start by talking about matchings in graphs, which is a very classical problem. We have the so-called marriage problem. Here the scenario is we have a group of women and a group of men, and some pairs know each other and some don't. And the question is whether they can all be matched up. So you see this is a rather old-fashioned problem as illustrated by my picture. The question presupposes that there are only matchings possible between men and women. There are no same-sex couples. So this is represented by a bipartite graph. There's one class of vertices representing women, one representing men. Edges represent pairs that know each other. And the question is about the existence of a perfect matching, which is a set of edges such that every vertex is in exactly one edge. Okay, so after we've answered that question, a follow-up question would be, okay, is there a good solution according to some optimization notion? So one problem might be the assignment problem, where you have on the one side some jobs, and the other side some contractors. Edges come with numbers which tell you how much that contractor will charge for that job, and then your goal is to find a matching that minimizes the total cost. Or you might imagine in the setting of men and women that each woman has a preference order on the men, each man has a preference order on the women, and you want to choose a matching which is optimal with respect to that order. So this is the well-known stable marriage question. There's a big optimization literature, but I'm not going to say anything more about it in this talk. Instead, I'm going to be interested in more general objects, so let me fancifully call this a modern solution. So we might allow same-sex couples, so now we're just talking about matchings in general graphs, or we might think about not just pairs, but groups of any size. So this is the problem of hypergraph matching. Okay, let me continue with graphs. I see the top of my slide is being cut off. Is there any way to focus in a bit? No? The top of my slide is being cut off. It's okay, it's just the title. Hall's classic theorem of Hall gives a characterization of matchings in bipartite graphs. So we go back to the setting of men and women. There's obvious necessary conditions. Every woman must know at least one man, every pair of women must know at least two men, and so on. So Hall's theorem is that these necessary conditions are also sufficient. One consequence of this is a simple minimum degree result. So if I tell you that every woman knows at least half the men and every man knows at least half the women, that gives you a perfect matching. This is also true in a non-bipartite setting. If I have any graph on n vertices, not necessarily bipartite, I should assume the number of vertices is even, because of course there'd be no perfect matching otherwise. And if every vertex sees at least half the others, then this guarantees a perfect matching. And this is you can't reduce the number n over 2, and there are a couple of examples here to show why. I'm going to go over these carefully. Although they're very simple, they're somehow the simplest instance of two very general phenomena, which I'm going to talk about in more later in the talk in more generality. So in the first picture on the left, the reason that there's no perfect matching is that there's a small hitting set. There's a set of size slightly less than n over 2 that intersects all of the edges. So So if you imagine taking a matching, every edge takes at least one vertex from that set. So the total number of edges you can take is at most the size of that set. I chose that to be less than n over 2, so no perfect matching. Okay. Second example is just two disjoint cliques, and I imagine that one of them has an odd number of vertices. There's an obvious parity obstructions of having a perfect matching. So two simple examples to show that the minimum degree bound cannot be reduced. Okay, this was all about graphs. Now I want to move to the setting of hypergraphs. I'll go through the definitions for anyone who hasn't seen hypergraphs before. So a hypergraph is just like a graph. There are some vertices, there are some edges, but now an edge can be a subset of the vertex set of any size. It doesn't have to be a pair. We'll be particularly interested in the case when all edges have the same size, R, in which case we call it an R graph. So a 2 graph is just another name for a graph. A matching is a set of edges such that every vertex is in at most one edge. And if every vertex is in exactly one edge, we call it a perfect matching. So in general terms, the question which we're interested in, here's a hypergraph, does it have a perfect matching? And we're just interested in a decision problem. For graphs, this is a classical theorem of Edmonds, or a classical algorithm, which gives a polynomial time way of checking whether there is a perfect matching. But for hypergraphs, it's an NP-complete problem, even if you just assume all of your edges have size 3. So we don't expect to have nice characterizations of the kind which I described before, unless we impose some extra conditions. So what kind of conditions might we be interested in? Maybe it becomes easier if we add more edges to our hypergraph to find a matching. That naively, that makes sense. But you think about it a little, you see it doesn't, because I can just take any hypergraph and take a disjoint union with a large clique, and I'll have many edges, and it doesn't make any easier to answer the question. So a better question would be to ask if there are more edges everywhere in a certain sense. So I'll make that precise with a definition. So we have a k-graph G. For any subset S, I'll define its degree. I'm denoting that size of G of S, the size of the neighborhood of S, or the link, but just the number of edges containing S. And then we have a range of minimum degree parameters. So for a graph, I just had 1 degree, but in general, there's a range of degree. For any number I, you can look at the minimum I degree, which I'm denoting delta I. And this is the minimum degree of any set of size I. And here I'll be particularly interested in the case that I equals k minus 1, one fewer vertex than the size of the edge, and that's called the co-degree. So let me write PMKC for a decision problem. You're given a k-graph with a minimum co-degree condition. You're told that every k minus 1 tuple is contained in at least c times n edges, n is the number of vertices. And the question is, does it have a perfect matching? So if C was 0, then I haven't told you anything. It's NP-complete. The Szymanska showed that it remains NP-complete as you increase this number C all the way up to a number 1 over K. With Knox and Mycroft, we showed that this number 1 over K is in fact the hardness threshold for this problem. Once you go above this problem, it becomes a polynomial time question. So I've stated this as an algorithmic result. It's fundamentally a structural result. We want to characterize the structure of hypergraphs which are above this threshold but do not have a perfect matching. And so now I'm going to go back to the ideas of space and divisibility which I mentioned for graphs and tell you what they mean for hypergraphs. So let's start with space. So now we're thinking about k-graphs. Edges have size k. I'm going to have some subset S of the ground set. There are n vertices, and the size will be slightly less than I times n over k for some number I. And I suppose I have the property that every edge takes at least I vertices from that set. Okay. What can I say about a matching? Every matching takes at least I vertices from that set, and you can't use any vertex more than once. So the size of your matching is at most the size of the set divided by I, which we've chosen to be less than n over k. So there's no perfect matching. You need n over k edges for a perfect matching. So this is one obstruction. Next obstruction is divisibility. So I mentioned the parity example for graphs. What does it look like in general? In general, I have a partition of my vertex set into some number of parts. Let me call that D. And we have a lattice, an additive subgroup of Z to the D. And for any set, I'll define its index vector living in Z of D. It's a vector that just records how many points it has in each of those sets. Now, suppose I have a hypergraph with the property that the index of every edge is in the lattice, but the index of the whole vertex set is not in the lattice. Well, if I look at any matching, the index of the vertices it covers is just the sum of the indexes of its edges, so that's going to lie in the lattice. But if I chose the vertex set to not have an index which is not in the lattice, then there can't be a perfect matching. So this is the generalization of the parity obstruction I described before. So here's a theorem of Knox and Mycroft, which illustrates one of these divisibility obstructions. It's also a parity obstruction in the simple case of 3 graphs. So somehow this, if you just go from 2 to 3, things become a bit more complicated, but not hugely so. It's analogous result doesn't hold for 4 graphs and higher, but for 3 graphs it's particularly nice. So what we're doing, we're looking at a 3 graph where the codegree is slightly larger than this threshold of n over 3 that I mentioned before. And I want to give you a structural characterization of when it doesn't have a perfect matching. And the answer is it's witnessed by one of these parity obstructions. There's a partition into 2 parts where one part has odd size, and every edge has an even number of vertices in that part. So the decision algorithm in this case is to search for such a partition. You may object that there are potentially exponentially many partitions, but actually the code degree makes it easy to efficiently search for these partitions. Another comment on this theorem is from the perspective of extremal combinatorics. So you might think a more basic question would be, well, what is the code degree threshold for a perfect matching? So this is a result of Rödel, Rosinski, and Semeredi, which I'll also mention later. So their result is that the threshold is about n over 2, and precisely it's given by this parity obstruction. So this is a stability result, saying that as soon as you're above a code degree of n over 3, the only way to avoid a perfect matching is to be contained inside the extremal example. Okay. I want to tell you something about what goes into the proof of the structural result. So it comes from a more abstract setting, which is thinking not just of the hypergraph, but also the simplicial complex in which it lives. So it's helpful to think of this graph as being the top level of some simplicial complex, and to have to relax the degree assumption to not just being a codegree assumption, but to think about a condition on how you can bubble up through this simplicial complex. You start at the empty set, you choose a vertex, you extend it to a pair, and so on. You want a lower bound on the number of ways to build an edge. And so with Mycroft, we'd shown a characterization of the perfect matching problem, where you're interested in finding a matching in the top level of a simplicial complex. And subject to a degree sequence condition of this kind, which cannot be relaxed in any way, we can characterize the existence. You either have a perfect matching, or you're essentially you have a space obstruction or a divisibility obstruction. So I think it's quite interesting that from this combinatorial setting, these geometric obstructions emerge. There's the divisibility barrier, which is obviously geometric or arithmetic. It's about the integral relaxation of your problem. And the space barrier, as I described it before, is not obviously geometric, but in fact it's about the fractional relaxation of the problem. It's about a problem in convex geometry. So somehow these are natural obstructions which emerge from in this problem. So this theorem has various applications. So there's the structured theorem I mentioned on the previous slide. We also found an application in extremal combinatorics, which was to determine the codegree threshold for finding a packing of tetrahedra. For those who know some extremal combinatorics, this is quite surprising because it's very much open to say anything about the existence of one tetrahedron, the threshold for that, or either codegree setting or even the extremal setting. And there's many other applications, I think, that could be discovered for this theorem. The proof of this is also the culmination of a lot of theory. It starts from the hypergraph regularity theory developed by Gowers and independently by Rödel and collaborators. And then also a blow-up lemma for hypergraphs that I proved later. So it's I think some nice theory that goes into this this result. Okay, so next I want to switch gears a bit and talk about the decomposition problem. So we'll be interested in questions which vaguely look like, here's an object A, can I decompose it into copies of an object B? So let me give you an example of this. So let me start with the picture, the well-known picture of the Fano plane. 7 points, 7 lines. Lines have 3 points. Every pair is in a unique line. From a graph theory point of view, I would like to think of the lines as representing triangles. And so then I'll think of that as a decomposition of the complete graph on 7 vertices into triangles. So I've partitioned the edge set into triangles. And then it's natural to ask, well, when can you do this in general? I've got some big complete graph, Kn. I want to decompose its edges into smaller complete graphs. I'll denote the size of the smaller one by q plus 1. So this is a problem which has many guises. It's in the design of experiments. It's I don't want to say too much about it, but there's an inequality there which quickly leads you to an inequality that must be satisfied. It's to have a hope of this decomposition, m must be at least q squared plus q plus 1, and you recognize this as the number of points of a projective plane. So how is this related to the perfect matching problem I've been talking about so far? There's a natural auxiliary hypergraph in this problem. It's actually the same one that Rob Morris mentioned in his talk. So if you're thinking about decompositions into triangles, so you start with a complete graph, and in your hypergraph you're going to have a vertex for every edge of your complete graph. And for every triangle of your complete graph, call it ABC, you're going to have an edge of your hypergraph which contains the pairs AB, BC, and CA. If you think about it, the problem of decomposing into triangles is exactly the same as finding a perfect matching in this auxiliary hypergraph. But this is a very sparse hypergraph. The one I just described has n squared vertices and only n cubed edges, despite that it has edges of size 3. So it's quite a different kind of problem. Okay, just from these simple beginnings, we quickly run into a big open problem for decompositions or design theory, which is when can you achieve equality? When is it possible to achieve the minimum bound? So there's a conjecture known as the prime power conjecture, which says this is only possible if this number q is a prime power, which is presumably motivated by the fact that we only know how to do it with projective planes, which are constructed by algebraic means. Another perspective on this question is, say, let's fix the number q and ask for which n we can solve the problem. And maybe let's assume that n is large to avoid the issues related to the prime power conjecture. The starting point would be to look at the case q equals 2. So we're thinking about when can you decompose a complete graph into triangles. So this was answered by Kirkman in the 19th century. There's some obvious necessary conditions that n must be congruent to 1 or 3 mod 6. And he showed that these are sufficient. So these are objects which are now known as Steiner triple systems. This is a historical accident because Steiner actually asked about them after Kirkman's work. Okay, let me continue with triangle decompositions and ask more generally, when can I decompose a graph, any graph G, into triangles? So I mentioned that there were some obvious necessary conditions. Let me explain those in more detail. A triangle has 3 edges, so your graph had better have a number of edges divisible by 3. Every vertex is degree 2 in a triangle, so certainly you need your graph to have vertices of even degree. So then let me give a name to this property. I'll say the graph is tridivisible. So Kirkman's result is just that you can the complete graph Kn has a triangle decomposition if and only if it's tridivisible. Okay. Can this be extended or not? It's not true that any tridivisible graph has a triangle decomposition. For example, a 6 cycle is tridivisible, but doesn't even have a triangle. What about quasi-random graphs? Here's a notion of quasi-randomness. If I have a graph on n vertices with density d, if the edges were random and I expect every vertex to have degree about the density times n, and I expect every pair of vertices, the number of common neighbors, to be about the density squared times n. So if that holds, then we say the graph is C-typical, where the parameter C is measuring the multiplicative error in this approximation up to a factor of 1 plus or minus C. So this is a well-known quasi-randomness condition. It applies the condition which appears in Semerani's regularity lemma. It's a bit stronger because it also gives you local information, which is, it's not surprising that we want to assume this. If you want to ensure that you cover every edge by a triangle, you'd want to know that something which guarantees that here's an edge, can I find a triangle? I need common neighbors. Okay, so a few years ago, I showed that Kirkman's result does indeed extend to the quasi-random setting. I won't state it precisely, but roughly speaking, this result is that if you have a graph that's dense and typical and tridivisible, then you can find a triangle decomposition. And this result has some applications. So one is, let's say you're looking at the usual model of a random graph and you want to know, can I decompose that into triangles? Well, you can't, because there will be vertices of odd degree. With high probability, about half the vertices will have odd degree. And the best you could hope to do would be to leave a perfect matching of uncovered on the vertices of odd degree. And conversely, you can do that, because it's not hard to show with high probability there is a perfect matching on the vertices of odd degree. You remove that, you do some fiddling to make the number of edges divisible by 3, and then the theorem applies to tell you what remains can be decomposed. And another application is to a conjecture of Wilson on the number of triangle decompositions. The formula is maybe not so important. What's maybe interesting is that there is a formula. This formula arises naturally from entropy considerations. So it was shown by Lineal and Luria that if you consider a random decomposition, so they gave an upper bound on the entropy, which gives this part of this result. So what remained to be done in this result was a lower bound. And the idea of the lower bound is that you can, if you want to find many triangle decompositions, you can consider a random process where you're starting with the complete graph, you pick a random triangle, you remove its edges, you keep going. At each step you have some graph, you look at its triangles, you take a random triangle, you remove it, and so on. You run this for a long time until there are very few edges left, but still enough such that my theorem applies to say there is a way to complete the decomposition. And analyzing the random process, which was done by Bowman, Friesen, and Lubetzky, gives you a lower bound on the number of decompositions, which matches the upper bound up to this lower order term. So I've been talking a lot about the triangle decompositions in graphs. Now I want to generalize and think about hypergraphs. So now the general setting is I have two R graphs, hypergraphs in which edges have R vertices, and so call them H and G, and I'm interested where can I decompose G into copies of H. So two cases of a particular interest are when we're thinking about complete hypergraphs. So let me write KRQ for the complete hypergraph on Q, complete R graph on Q vertices. The question of whether you can find a KRQ decomposition of KRN is exactly the question of Steiner, which is whether you can choose a collection of sets of size Q on a set of size N such that every set of size R is contained in exactly one. More generally, you could introduce multiplicities on the edges, have every edge appears with some multiplicity lambda, and then you have the general problem of the existence of designs. So this decomposition problem specializes to the existence of designs. What are the necessary conditions? So I mentioned these divisibility conditions for triangles. How do they look in general? They arise in the same way. Imagine I'm decomposing G by copies of H. Let's consider any subset E of the vertex set of G. So it has some number of edges. That number is called its degree. And for every copy of H, which I'm using, which is sitting on top of E, I'm going to use some number of edges. That number is going to be the degree in H of some subset F of the same size as E. Now, there may be various different degrees, but somehow you need to partition the degree of E into these degrees in F. So a necessary condition is that the degree in E must be divisible by the greatest common divisor of all of those degrees. So that's a necessary condition. We call that being H divisible. So the existence conjecture raised by Steiner in the 19th century which I proved a few years ago, is that this is essentially about divisibility, at least if you assume the number of vertices is large, and this is a necessary assumption. We know that it's not true for rule n. So this result, so I've phrased it in terms of decompositions, but another way to phrase it is that designs exist for large n compared with the other parameters, q, r, and lambda. And this conjecture has a very long history. I'm not going to have time to go through all it. I should at least mention that it was proved in the case r equals 2 by Wilson, and I'll mention an important contribution by Rödel, the existence of almost designs. I'll say more about that a bit later. And then, so you might ask what's going on more generally, and also about the typicality generalization. I mentioned my result on the typicality generalization of Kirkman's theorem on triangle decomposition. And this holds in general as well. I'm not going to tell you what typicality is for hypergraphs. You can imagine some definition which is similar to the one I gave in graphs. And it is true that dense typical hypergraphs, if they satisfy the divisibility condition, then you can find a decomposition. So I proved this in the case of cliques, and then this was generalized by Glock-Kuhn-Lowenotthus to general hypergraphs. Now you might wonder what happened to space in this problem. So I've been talking a lot about divisibility. So somehow in this setting, if I'm thinking about a complete object or a typical object, the issue of space doesn't really arise. Everything is uniform. But there is a generalization which takes that into account as well. Really, there's a more general theorem which says that really this problem is just about the fractional obstructions and the integer obstructions. So in this case, it really parallels the theory for the dense case, despite the fact that this is about certain sparse hypergraphs. Okay, so I want to tell you some ideas that go into the proofs of these theorems, at least at a very high level. So it starts from the idea of the absorbing method. So this is an idea pioneered by Rödel, Rosinski, and Semeredy for perfect matchings in dense hypergraphs. And I'm going to illustrate this for the problem of finding a perfect matching in three uniform hypergraphs, three graphs. So I mentioned this result of Rödel on the existence of almost perfect matchings. This is a fundamental starting point. There's this semi-random method, or nibble, which is very important throughout combinatorics. And what it tells you in many problems of interest, such as the existence of designs, you can cover almost all of what you're trying to do. So it's really, the question then comes about how do you deal with a small set which you haven't managed to cover? How do you make a transformation to turn an almost perfect matching into a perfect matching? And the idea is that before you start, you put aside some magic set of edges which you're going to have nice modifications which you can use later. So these are the ones I've labeled, the red edges labeled reservoir on the right of the picture. So I put aside this nice reservoir, and then I apply Rödel's method to find an almost perfect matching on what remains. And then I have in the center I have a small set of vertices, blue vertices, which I've labeled leave. These are the ones which I haven't managed to cover. Somehow I have to deal with them. The nice property of this reservoir is that it can absorb any triple. I'm talking about three graphs, so it will be a triple. And this is illustrated by the green picture. For any set of three vertices in the leave, I can find two red edges in the reservoir, and I can throw those away and replace them by the three green edges in the picture. And I've made an improvement. I've still got a matching, and I've picked up those blue edges, and I can iterate this process until I have a perfect matching. So this is the idea. How do you find that reservoir? So for dense R-graphs, for example, the result I mentioned of Rödel, Rosinski, and Semeredy on the threshold for perfect matching, it's enough just to take a random matching. You can then analyze that and see that with high probability there are many absorbers. This is not going to work at all for sparse hypergraphs, such as the ones in the existence of designs. If you choose things randomly, you just don't get any nice configurations. So it seems hopeless, but in fact, this was the idea of this, nevertheless, in the idea of the second proof of the existence of designs given by Glock, Kuhn-Lowenotthus. They found a way to make this idea work, even in the sparse setting. Somehow there's a complicated way of gradually reducing the leave until it's possible to make this idea work. But let me tell you about the method which I used a different method for resolving this problem. And this is an idea of randomized algebraic construction. So this starts from the observation that algebra does very, very well at constructing designs in many cases. And for a long time, people believed that such highly symmetric objects could really only come from algebra. And the point is that you can, if you have some abelian group, a finite field, you have some equation, solutions of equations in that, they have nice regularity properties. Or if you have some group acting on a space, they will have these regularity properties. And so on the right-hand side, I have a picture which I've labeled template, which is going to be the reservoir in this approach. I'm going to illustrate this idea, I'm going back to the problem of triangle decompositions of graphs, and I'm drawing my graphs in a funny way just to make the pictures a bit easier to see. If I try to draw triangle decompositions of graphs correctly, you would just see a mess, a graph with lots of triangles overlapping each other. So imagine that I can just draw the edges disjointly, despite the fact that some of the edges have common vertices. So I've drawn lots of triangles on the right, and the way I obtained these triangles was I consider a random embedding of my vertex set into a finite field, and I'm going to take all of the triangles x, y, z, which satisfy this equation, x plus y plus z equals 0. So we observe that this equation, for any x and y, there's a unique z that solves it. It may or may not define a triangle, but there's going to be a most one triangle. So I'm going to get some set of edge disjoint triangles living in my graph, and you can show that they'll cover a positive fraction of the edges. And this is going to be good enough for doing the absorption step later. Okay, so now we continue as before. There's the Rödel's method, nibble method of covering almost all of the other edges by disjoint triangles, and then we have the leave, which is some small set of edges which we haven't covered. Next, it's convenient for me to transfer the problem from having edges which are not covered to having edges which are covered twice rather than once. So I'll choose some small random set of triangles which cover the leave and they spill over onto the template. So now, after I do this, I'm in a situation where every edge is covered at least once, and there's a small number of problem edges, the spill, which are covered twice. And the question is, how can I resolve that? So here's some pictures to illustrate the idea. So the first step at the top of the slide is imagine what would a solution look like. What would it look like? I'm going to have to find some set of triangles in the template. These are pictured on the right-hand side. I want to throw those away and replace them by some new triangles in such a way that the difference in the edges which I've covered is precisely the spill, the problem edges. If I would succeed in doing this, then I would reduce the multiplicity of those spill edges from 2 to 1, and I would have a perfect decomposition, which is what I want. So another way of thinking about this is it's an assignment of weights to the triangles. I'm assigning weights 1 to the triangles on the right, weight -1 to the triangles on the left. And if I sum up the weights on any edge, I get 1 for every edge of the spill and 0 otherwise. So this is suggestive of thinking about the integral relaxation of the problem. So the triangle decomposition is a 0-1 problem. I assign weight 0 or 1 to a triangle. I want to make the weight on every edge equal to 1. Suppose I allow myself any integer coefficients. This is a much easier problem to solve, even in full generality for hypergraphs. This goes back to work of Wilson and Graefer and Gervat in the 70s. And so one key step in my approach is to generalize their work on integral decompositions to the quasi-random setting, and also to show that you don't need to use all integers. You can just use -1, 0, and 1. But we're not done yet. So the key, there's one important point which I haven't addressed, which is these triangles on the right, which I'm assigning weight 1, they must come from the template. And this is a very special set of triangles which I fix in advance. When I solved this problem originally, I was thinking about all n-cubed triangles, but there are only n-squared triangles in this set of edge disjoint triangles in the template. It's very hard to use any of those, at least a priori. And this is really why a random construction would fail. You could do all this with a randomly chosen template, but when you get to this step, you would run into trouble. So why is it going to work? So the idea is, imagine that I want to use some triangle, x, y, z, in this on the right, but I can't because it's not in the template. So instead, I would look for a picture which is illustrated at the bottom right. So I'm showing you the octahedron drawn on the plane and two different triangle decompositions, the red triangles and the white triangle, where the desired triangle XYZ is the external face of this drawing. So these cover the same set of edges, and I can freely pass between them if they are present. So if those red triangles happen to be present as triangles in my graph, then they would be included in the template, and I would be able to remove them and instead take the white triangles, and I would have this desired triangle XYZ. So what's going on here is there is this octahedron which has this labeling. I forgot to say when I described this that I'm going to work over a field of characteristic 2. So if I look at x, y, and x plus y, that's a zero-sum triple. And so if you look at how I've labeled the red triangles, they are indeed all zero-sum. So despite the fact that this finding an octahedron in the triangles I've chosen is something which just wouldn't happen if I'd chosen those triangles randomly, once I can impose these algebraic constraints, it becomes a very something which occurs with positive density. So it's really about imposing the right constraints so that what you want is then a positive density configuration. Okay, so to conclude, what I've been telling you about so far is about results from a few years ago, but I also wanted to mention some more recent results, which I'm not going to go into in great detail, but I was able recently to generalize these results to solve many other problems in design theory. So one of these is the question of resolvable designs. This goes back to really a classic question in design theory, which is the Kirkman schoolgirl problem, which maybe some of you came across. This question about you have 15 schoolgirls, you want to arrange them so that every day they walk in 5 rows of 3, and they should do this every day for a week, and every pair should walk together exactly once. So in the language of decompositions, I'm interested in finding a triangle decomposition of a complete graph with the extra property that its triangles can be decomposed into triangle factors. A triangle factor is a partition of the vertices by triangles, so n over 3 vertex disjoint triangles. It was open to find the hypergraph generalization of this, and that was something which I was able to resolve recently, and also various other problems in design, such as decomposing hypergraphs by designs, or complete hypergraphs by designs, or more generally decomposing designs by other designs, and various other applications. I put a survey on the archive recently if anyone would like more information about that. Another comment is on it's very interesting philosophically that these constructions are essentially random. That they come from this Rödel method, this semi-random construction, and then there's this really accounts for most of the edges, and there's just some small modification about how to turn an almost decomposition into an exact decomposition. So this is interesting for various reasons. One is this fact in itself has applications, such as the existence of bounded degree high-dimensional expanders in a certain sense. So this is quite related to the question posed by Lubotsky this morning. And indeed, he's one of the co-authors on this result I mentioned. It's also interesting that it really goes against this classical idea that these highly symmetric structures must come from algebra. These are highly symmetric. These properties, they have these nice properties. They're almost entirely random, and so maybe it casts doubts on some of these other conjectures which have an algebraic motivation, such as the prime power conjecture. Also, from a practical point of view, my proof gives a randomized algorithm, so it's perhaps feasible to implement this and actually find designs. We do not actually know explicit designs for when the number r is 6 or 7, or 6 we know, 7 we don't, so this would be interesting. Let me mention some of the main open problems, at least in my opinion. So that I've mentioned the prime power conjecture. Another conjecture with a similar flavor goes back to Hadamard, and this is about the existence of matrices whose entries are plus or minus 1, which are scalings of an orthogonal matrix. There's some obvious necessary conditions, and it has to be 1 or 2 or divisible by 4. And the conjecture is that these are the only conditions. So it's quite interesting that this conjecture reflects the opposite philosophy to the prime power conjecture. It's not the conjecture, the examples we know exist, but somehow the conjecture is about there are examples, we just don't know what they are. These are questions about designs with large blocks. I haven't really explained what this is, but when I've been talking about decomposition so far, I've been thinking about decomposition into very small pieces. So these are kind of the other end of the spectrum. But there's still many interesting open problems about decompositions with small blocks. And I think one of the most important is the conjecture of Reiser, which is usually phrased about the existence of transversals in Latin squares, but I want to phrase this in terms of decompositions. So this is a question about taking one kind of decomposition and finding another inside it. So I'm going to think about a triangle decomposition of a complete tripartite graph. So this is the same thing as a Latin square. The conjecture is, so if n is odd for any such decomposition, you can find within it another kind of decomposition, a triangle factor, which I mentioned before. This is a decomposition of the vertices by triangles. I think this is a very appealing conjecture. I should mention n odd is necessary, but if n is even, you should be able to almost do this. And just to round this off, so now that we know the existence of designs and decompositions for hypergraphs in general, it suggests that we should be investigating the theory of these objects from various perspectives. So from an extremal perspective, there are many natural questions to ask. So maybe the most basic is just the threshold for the existence. What degree conditions you need to guarantee decompositions? And from the probabilistic perspective, there are also several natural questions. I've just mentioned a couple here. So we can ask about thresholds. If I take a random 3 graph, for example, what's the threshold for finding a Steiner triple system? And what can we say about random designs, say a random Steiner triple system? Can we say develop any kind of theory which is analogous to the theory of random graphs? Okay, I'll stop there.
Are there any questions? No questions? Could you say something about counting, approximate counting?
Yeah. So so for example, the number of Latin squares. This is a classical result of Van Lint and Wilson, which comes from the celebrated results on permanence, the Van der Weyden and Mintz conjecture. But there are natural higher dimensional generalizations of this, so the counting of higher dimensional permutations or Latin cubes, which was open. So Linnell and Luria gave an upper bound. There's a natural entropy bound, and they conjectured that this was tight. And indeed it is up to the lower order term. So this follows by a similar kind of argument to the one I showed you the one I very briefly alluded to for the number of triangle decompositions. It's this analogous question. I'm interested in decomposing a apartheid hypergraph into copies of, in general, any hypergraph. And you can run the same random process and show that it can be completed by a similar kind of proof. So this shows the existence of, shows the approximate counting for high dimensional permutations and various other configurations as well. It gives you an approximate formula for the number of Sudoku squares of any dimension as well.
Any questions?
Yeah.
Ah, yes.
Could you explain once more the Reisner conjecture related to Latin scale?
I'm sorry, which one?
Reisner conjecture related to Latin scale. Explain one more time.
The relation to Latin squares, yes. So if I have a Latin square, so it's a square, n by n square, which is filled by the numbers 1 to n, then I can make a 3-partite graph where one part is rows, one part is columns, and one part is symbols. And then for every triangle, I can make for every symbol in the square, for every square, I can make a triangle where I just make a triangle joining the row, the column, and the symbol. And so in that way, the definition of Latin square exactly translates into a triangle decomposition of a complete tripartite graph. So that's the translation. And then if you see what is a transversal in a Latin square, so this is a set of cells that use every row, every symbol, and every column exactly once, that's exactly the same thing as a perfect matching in this auxiliary hypergraph. So really, these are the same question.
Okay, if there are no more questions, let's thank Peter again.